So I'm going to do this. I'll take one, maybe two questions, then I'm going to go through some new material, and then we'll have our quiz. Now, somebody came to me and asked me if we could postpone the Friday quiz till Monday. If you'd like the Friday quiz on Monday, would you raise your hand? I don't think I need to count. Thank you. I'm very flexible about stuff like that. All right, next. I want to do at least one problem, maybe two. So do you have a problem you'd like me to do? Yes, sir.
2.42, please.
All right. Can you give me the specs?
Yes, sir. Z load is 70 plus 110 J ohms.
Hold on. Z load, and this is 70 plus J 110 ohms. Go ahead. What's Z on?
50 ohms.
50. Go ahead.
And then, yeah, that's it. That's all the
What do they want?
They would like the distance from the load to the open-ended shunt stub.
Oh, so this is an open. All right, so now open end looks like this. It means it's not shorted. It's like this. It's an open stub, or open circuit, I would put it this way. Open circuit, right? And we want this length, I just call it L stub. And we need this distance here, which is going to be L. I'll call it just L through. Okay. It doesn't matter. All right, y'all with me, class? Everybody understand the problem? So now, what we're going to do is start here with the open circuit stuff. Do you all agree it's in parallel or shunt? Class?
Yes.
It's not series, right? Shunt? Correct. If it's shunt, we're going to work in the admittance domain. You all hear me on that? Now, do they want this length minimized or this length?
Minimize the length of the stub.
All right, so they want the stuff to be as short as possible. So we're going to examine this right now.
Sorry, not length of the through line.
Oh, okay. So they want this to be minimized. All right. That's an easy problem in a sense. Okay, y'all hear the problem? Understand that we're trying to have the distance from the load to the point where the stub is attached to be a minimum. It isn't shunt or parallel, so we work in the admittance domain. Y'all hear me? Now, let's start with this right here. So I'm going to do my pseudo-Smith chart right here. I always put the one circle in. This is infinite, and this is 0. This is J1, and this is minus J1 here. And now, first thing we always do when we do these problems is what, class? Normalized load, which is ZL over Z0. So that's what, 70 over 50 or 1.4, right? And it's 110 over 50 plus, J, what is that, 2.2 plus? Y'all agree with that?
Yeah.
Now we have to locate that point, the next point. So, and if you don't understand something, now's the time to ask. So if you look at this, we have a real circle of 1.4. This is the one circle. 1.4 is somewhere in here. You're going to have to estimate it yourself. Do you all agree with that? Everybody follow me on this. The J2.2, this is J1. J2.2 is about here. So where these two intersect would be the load. So this would be ZL. Y'all with me? On a quiz, what you do is label 1 there. That way I know you came into that point. Now after that, you take in, the order here doesn't matter. Take, what I normally do is draw a straight line from the center here, center of the circle right through that, and you're going to get something wavelengths towards generator. You can give me that in a second. But at the same time, take your compass, and I assume everybody has a compass here, you'll need one. And then draw a circle like this, a constant radius. This is the reflection coefficient magnitude right here. Go ahead and do that. Y'all with me? I want you to be real, I want you to listen carefully. They want the actual distance from the load to where the stub is attached to be a minimum, okay? Now, when we do this, whenever we're looking for where we're going to attach the stub in terms of the location, there are two possible points, and I want you to hear me. We're at this point, as we move wavelengths towards generator, we're going here. Here's the first point. I'm not going to throw this here. I'll throw it up there. Very good. All right, but you're going to move this way, right? This is the movement. You're at the load. You can only go towards the generator, right? The other one? Oh, wow. This is just part of. Perfect. All right, we come down here. Now, you all see this is the first point we hit. You all see that? It's got to be at the one circle, because remember, that's the key, but that's in the what? The impedance domain, right? That's this. I'm showing you the typical mistake. You all hear me on this? When we're at ZL, if we're going to put a parallel or shunt stub, we got to go right to the impedance domain. So this is a common mistake, and if you did that, you're not alone. You all hear me? So to go to the admittance domain, we wouldn't do that. We take a line, go straight through here, right? Y'all hear me on this one? We're going to work in admittance. So here would be the point, that would be point 1 here. This would be point 2. And YL is simply 1 over ZL normalized. Can you give me the location of that, please?
0.22.
0.22.
Minus 0.32J.
Minus J 0. Say that again?
32.
32. All right. So that's our second point. It's really the same point, but now we're in the admittance domain. This would be the natural progression. Do y'all follow me? I'm going to say this right here. Make sure you do. It's a great problem, too. Now, we want to move a minimal distance from here, right? Until we hit the one circle. That would be this point here. You all see that, class? Right? This is a common mistake. People will move here. They'll think impedance, move to that point. It's admittance because we're in parallel. I mean, it goes shot. So now, at this point, I'm going to just do this. Try to draw a straight line through here. This point, I'm not even going to bother with that. This has a certain wavelength towards generator location, and this point down here has a wavelength towards generator location. Can you give me this location of where the YL would be? I just need you to do this. Please get a Smith chart out and make sure you can see this on your Smith chart. Yes, sir.
0.448.
0.448 lambda, right? Y'all agree with that? All right, we've got to move to this point. Can you give me this location right here?
I have a question on that. Does it matter if you choose 1 plus JV or 1 minus JV?
Yeah, because he said he wants the distance a minimum from the load, right?
Sure.
So it would be the first point that we hit, because that would be the shortest distance. Do y'all follow me on this, class? All right, now, I mean, there's another point we could hit. We could hit down here, but that's further away.
Okay, so for minimize the through line, you go
It's
to
the first zero you hit, and if it's if you're moving, if it's a shunt or parallel stub, then you're going to go to the Y domain first and move until you hit 1 plus or minus J, but it's got to be in the Y domain, all right? Yes, go ahead.
I can't see it. Thank you.
Sorry. Yeah, get me out of the way, just shoot me over. Y'all with me, class? In the back, can you guys see it back there? All right, now, at that point, I need this distance, wavelengths towards generator, where you go right through that one. Why don't you give me the, what is this, 1 plus what? 1 plus J what?
1.9.
1.9? Anybody confirm that?
Yes, sir.
All right, now give me this, if you take a line. I'm not sure I really need this microphone, but you insist.
That's why it definitely helps with the audio quality in the
All right,
video.
if it helps, I'll use it.
Thank you.
All right, now guys, what is this wavelength towards generator?
0.185.
Everybody confirm that? Lambda, right? That's in lambda. I want to make a point. Y'all hear me? That's fractions of a wavelength. Now we're going to find the distance right here, this sloppy little thing that I put down here, L through. We're going to find the distance, right? So the L here, I'll just call it L sub T, the through line. First you find the location you ended up at, right? It's point 185. Then you subtract the location you came from. Think of mile markers on a highway. It's the easiest way to do this. So this is point 448. Right? But it's negative. You agree? So what do we do, class?
Add 0.5.
Add a half wavelength, we're at 0.5. And all this is times lambda, so what is this going to be in terms of lambda? Anyone?
0.237.
0. Say it again?
237.
7 lambda, is that right? All right. Now, hear me. Lambda is dependent on frequency. I want you to hear me. Hint, I want you to hear me. Lambda, if it's lossless, is the velocity on the line, phase velocity line, divided by frequency. This is assuming the line is lossless, and it will be for any stub tuning problem. You all with me? How many know that? If it is the speed of light, it would be c over f, right? So c is 3 times 10 to the 8th meters per second, isn't it, class? So if I gave you a frequency, you could determine the wavelength if the speed was c, right? If it was 2/3 c, then you would use 2/3 c divided by f. Does everybody hear me on this? Several problems I gave you included that dimension, and they were not in your book. Do you all remember those problems? I posted a bunch of them. How many remember that? All right, good, you did. Now, if you think about that, this is important. Let's assume this is 2, say, millimeters, right? Now, if we get this in terms of fractions of wavelength, what's the actual distance we would move? Well, it would be what? 0.237 times 2 millimeters, or what? 2 times 10 to the minus 3rd meters, right? And what's that? Well, that is a very small distance. Do you all hear me, class? But it would scale by the wavelength, and that's just something you have to know. People oftentimes draw blanks when I ask for an actual distance. They forget it's simply the velocity divided by frequency. Can you all hear me on this one? Make sure you know that. Now, back to this problem. So we've got the through line is 0.237 lambda. Is that correct according to the solutions?
Yes.
You asked about it, is that right? All right, remember this is parallel. So now we've got to find this distance, right? L stub. We've already determined that. We've got to get rid of, what is it? J 1.9, don't we, class? So we need to add a stub that has an admittance of minus J 1.9. You all hear me? Please pay attention to this. Now when we talk about the stub right here, well, this is a good problem. When we have a stub like this, and now this one's open circuit, it's not shut, and this is Z naught. What is the impedance of an open circuit?
0.
Impedance.
Infinite?
Infinite, right? Right? Isn't it, class? It goes to infinity. Nothing, no current can flow. Y'all with me? All right, now, that's impedance. We're in the admittance domain. What is the admittance? I mean, we normalize. Let's normalize the impedance. If you have infinity divided by Z naught, it is?
0.
Infinity. Infinity. Do y'all agree with that? All right, so it's probably for comic relief you're doing. Anyway, so we have 0, right? If we take, we're going to have infinity, no matter if we normalize it or not. 1 over that is going to be 0 for admittance, right? Where's the 0 point on the Smith chart, class? Right here, right? So how far do we have to move? I want you to think about it. Until we get minus J 1.9. Correct, class? It was plus J1, we got to nullify it. So we've got to go at least a quarter wavelength, right? Isn't that right? And now, somebody do this for me. How far down do we have to go? Until we have about here, J 1.9. Do you agree? So how far is that? No, this is nice because this is the 0 point measurement-wise with wave. So just look here and tell me what this is. Wavelength storage. Say again?
0.328.
Does everybody hear him? 0.328? You got that? 0.328 lambda, right? So that's just this distance, 0.238 lambda. Do you all agree with that? Now, if I wanted the actual length, you would multiply that 0.238 by the wavelength, whatever it is, correct? And wavelength is dependent on frequency. Do you all follow? Yes, sir.
Isn't it 0.328?
Sorry, 0.328. because I can't hear. 328. When? I'm sorry. Y'all, is that the right answer, class? How many understand that? Now, pay attention. I've got a question. So that's an open circuit, right? What if it was a short circuit stub? Just think about it before you say it. What if it's a short circuit stub right here? Now, what do we do for this? It's easy. Go ahead. Now, think about this. If it's a short circuit stub, what is the impedance? 0, right? What is the normalized impedance? 0, right? What is the normalized admittance? Infinite, right? So now, if it was a short circuit stub, you would start here, wouldn't you? And you would go to here. Or, in other words, it would be shorter. Do you agree with me, class? Or, you would just subtract the quarter wavelength from the prior distance. Do you all follow me? How many see this right here? In the back, can you guys hear me and see that? Y'all with me over here?
Oh, yeah.
Now, these problems, I want you to just understand, anytime you see something in parallel or shunt, always the admittance domain. If it is in series, then you stay in the impedance domain. All right, for capacitors and inductor calculations. You all with me on this? If they're parallel or series, you got to make sure you do it in the right domain. And that's it in a nutshell. The more problems you do related to this, the more confidence you'll have and realize that this is not hard. But if the less problem, I mean, if you just try to wing it, boy, you can get hammered. Yeah.
So there's a part B on this one.
Yeah.
And it says that they measured the load wrong, and it actually turns out to be something else.
They
And
want to
it
know
also-
what the input impedance is, right?
Yeah, they want to know what the reflection coefficient
Yeah,
is.
we can do that. All right. We're going to do part 2. I'm going to leave that up there. So what he says, let me go back to the open circuit stub right here. And these are the links, right? Now, here's what he says. Oops, we made a boo-boo. We messed up. Well, what's the value now of the actual load impedance? Y'all hear me on this, class? Now he's going to change something, which is wrong. Go ahead.
That would be 40 plus J100.
All right, so this is now 40 plus J100. All right, what is the normalized impedance of that? Well, it's what? It's 0.8, isn't it?
Yeah, 0.8
Plus
plus.
J2, correct? Now, just follow me on this. I don't think you're going to have any problem seeing this. So, do I have another? I should have red, but I don't have red. Is this one work? All right, we'll use this one. So where's that located? Where is 0.8 plus J.2? Well, 0.8 is something a little bit larger than this, right? And J2 is right about here. So if you draw this, I'm going to have to just kind of cut to the chase here. So this would be my ZL2, 0.8 plus J2. How many see this? Am I going to work in that domain? No, right? I'm going to go to the admittance domain because we're adding things in parallel. So when I go to the admittance domain, you're going to have to do this for me. Boy, I put it, maybe it's up here. Anyway, now you're going to have to draw a second circle. And this is really getting messy, but you all follow me. I locate the point, now I do another circle, and I also have to locate the point. I start up here, something wavelengths towards generator. Again, we're going to repeat exactly what we did at first. Oh, sorry. Actually, I'm not going to work here. I'm going to work over here in the admittance domain. So this point right here, which is 1 over that. Can you give me that value? This is YL2. Which is 1 over ZL2, which is 1 over this. So what is it? Let's take 1 over 0.8 plus J2. Anybody? If you did this one, do you have it, anybody? 0.8 plus J2, take 1 over that, somebody. It's not hard.
On mine I have 0.16 minus J 0.44.
0.16 minus J what?
0.44. Can any of y'all?
0.44, about that. Let's just go with that, all right? Now, after that, what I need is this. I need right here the wavelengths towards generator. Can you give that to me? You need to take a straight line from the center through that point. Tell me what that is.
0.433.
How many confirm that? Can you all see it or not? I mean, take a look. Can you see that? How many got that? I mean, really, how many understand? Let's try that. Do you understand, sir, over there, guys? I'm trying to make sure, because this is important. All right. Now, how far do we have to go? We have to go what? This far, right? Correct, class? So where's that going to be? Well, think. We're here, right? We're going to add that to it, correct? But it's going to be greater than a half wavelength, isn't it, class? So what do? Subtract the half wavelength. Tell me what that is, because it's going to be the same distance, but here's what you're really looking for. You're going to have the distance, let me do it here. The distance you're going to move is going to be 0.448 lambda, and it's going to be plus the length of that was 237, right? Now that's going to be greater than half a wavelength. Do you all agree with that? So we subtract the half a wavelength from it. And now that's your location in wavelengths towards the generator. We have to find, we're going to locate it. Go ahead. Anybody tell me what that is? This is a good problem.
0.185.
So this is 0.185 lambda. Now let's see. Is that right? Same exact point. Is this point right down here? Oh, did I add the wrong thing? Sorry. My bad, 0.433. I'm sorry. 0.433. I'm sorry about that. Now do it. I apologize.
0.17.
0.17? All right. So this is 0.17 lambda. Now we got to locate that point, wavelengths towards generator. It's up here, isn't it, class? This is 0.185. So this is 0.17. It's about here. So it's 0.17 lambda. Now you got to shoot a line right through there. Just like I did. Can you do this, class? You follow the method here? Now remember, these are admittances, right? All right, now you got to tell me what the admittance is at this point. This is a good problem. I know this is a messy Smith chart, but I'm a little pressed for time. Tell me what that is. It's not going to be 1. What is it? Can you all see it on your Smith chart?
What do you say to look for with that line?
I'm trying to remember, what you had to do was draw a circle of the radius of the second lobe, right?
Okay.
Y'all hear me? Give me 1 second. I want to fit. Y'all with me on this, class? Now, we don't go to the impedance domain, we go to the admittance domain. So we're down here. This is our starting point. Now we're going to move until we get 0.17 lambda on the outer circle, right? We're still moving along this constant reflection coefficient circle for the second lobe. But you got to give me the value that it is. I can't tell. Just yeah.
Did you want the impedance or the?
I want this point. This has got to be an admittance.
Okay.
Yeah. Y'all hear me, class? This is an admittance, right? This is location at the admittance that's going to be right here. Got it.
0.6 plus J 1.7.
Plus J what?
1.7.
All right. Can anybody confirm that as the admittance? Anybody? You got it? Class, you guys got it back there? Over here, Jeremiah? What?
Still working on it.
Take a moment. Make sure you convince yourself this is it. I want to make sure you see this. All right. Remember, what we're doing is we're in the admittance domain. We're not going to the 1 circle anymore. We're going to add from the point that we came in at, the y, we're going to add the length that we're actually going to move, because that's unchanged. You all follow me? Now, when we're here, right here, this is the normalized admittance here. You all hear me? Everybody hear me? Before, what was the normalized admittance we added? Minus J 1.9, didn't we? To get rid of the plus J 1.9 before, correct? That's still there. You all hear me? So now we add this, so we have this. That's the admittance there, and then we take minus J 1.9. Now tell me what that is. It's what? Did you say 0.64 before? It would be 0.64. That's the real part. The imaginary part is what? Minus J 0.2. Can anybody confirm that that would be the admittance you'd get when you add the prior admittance of the shunt stub? How many see that? You don't see it. What don't you see? Help me.
I think.
Whenever people say that, I get worried. In the Navy, when I was on the Eisenhower as a weapons consultant, you don't ever say, I think I got it. You know why? Because 50 caliber machine, actually they had 20 millimeter Gatling guns. Those things don't forget, man. You don't get a do-over. Somebody's dead or the ship is sunk or something. All right, now, really, can I help you? What are you feeling comfortable with?
No, I really do think that I understand it. Like,
How many do, honestly? I mean, if you don't, please ask a question. Don't be quiet and you have a problem. All right, y'all follow me what I'm doing. I'm using the same exact admittance that we calculated before to add, and I'm adding it to that. Now, that's the normalized admittance, right? What would the normalized impedance be? 1 over that. Do you agree, class? So this is the normalized admittance looking at this junction right here. This is what's right here when you combine the effects of the load that we added, it's a different load, and this shunt stub. That's the to get the normalized impedance, we take 1 over that. Let me just call this y prime. So the z prime, I'm doing it for this reason that you'll see. Do y'all agree it's 1 over y prime? That's the normalized impedance at that point. Do y'all agree with that? Now just listen to me. Now, we can do this 2 ways. If you want just the magnitude of the deflection coefficient, I don't know if you want magnitude and angle. But what we can do is this. We can take this point, wherever it is, I don't even know, but it's a new point. Do y'all follow me? That's admittance. Then go right to the impedance domain. Take 1 over that, or just draw a straight line through there, and go to the conjugate point here. That will be the magnitude, that line from the center to that point, of the reflection coefficient. You can read the angle down here, but it has to be done in the impedance domain. A second way to do it may be an easier. Do y'all follow me what I've done here? Simply take 1 over that y value. You can simply do this. You know, reflection coefficient is really equal to the impedance you're going into minus the impedance you came from, right? So this is equal to ZL, or it's the combined Z of everything. You can just say it's Z prime. It's the impedance you see at that point minus Z naught over Z prime plus Z naught. Now if you divide top and bottom by Z naught, you get Z, I'll call it Z prime minus 1 over Z prime plus 1. This is your Z prime, it's 1 over that. And you can get the right value doing that. You all see this, class. What is that value? Can somebody tell me? Give me the magnitude first and the angle. How many understand this here? In the back. You don't understand it, sir?
I'm catching up.
All right. The only thing you have to think about, at the point where these two connect together, there's going to be an admittance, normalized admittance. The sum of these two, that this impedance, this line sees over here, like a single load. To get the normalized impedance, just take 1 over that admittance. Now, that's the normalized impedance. To get the reflection coefficient, normally it's ZL minus Z naught over ZL plus Z naught. Because it's normalized, you can divide top and bottom by Z naught, then you get ZL minus 1 over ZL plus 1. That's what's right here. And you can do this on your calculator. What value do you get, anyone? Okay, can somebody give that to me? I need magnitude first. It should be in his book. But you should be able to calculate this, because if you can't calculate this and see it clear, you're going to get in trouble, a lot of trouble. Yeah.
I think it's 1.423 plus J 0.44.
No, give me magnitude. Magnitude. This reflection coefficient can't be greater than 1. Y'all follow me on that? If you got a 1 plus something greater than 1, you got a problem. There's something.
I got 0.25 and then an angle of 36 degrees.
Angle of 36 degrees. Anybody confirm that? Anybody at all confirm that? Is that what the solution is or not?
Yeah, I got the same answer.
You got that? Anybody else? Now this is a classic problem that I give on exams, especially the final, where I alter the actual value of the load after it's matched so that you'll have to know how to go about this. If you don't know, you really get hammered, all right? And there's very little partial credit and stuff like this. You really have to have a handle on. I'm just trying to encourage you to be sure you're clear about everything I did. With me? All right. I'm going to start a bit of new theory, but you're going to get your quiz in a second, all right? I want you to take a look at the next section on reflection coefficients. Now, you don't have a great interest in this right now for some reason, because there's a quiz imminent and it's not. I'll tell you what I'll do. I'll give you a quiz, all right? You'll have more than enough time. But on Friday, I hope everybody's here, about everybody's here, because I don't know what, but if I don't see everybody here, I'm going to do something all night. All right, just give me a second.
Here, I'll move here.
By the way, protect the great problem. This is a super problem.
I'll move next to Mason. I'll get you Mason to the party thing.
Okay, that's fine.
For your troubles.